Hi guys, I am Shubham Agrawal, and in today's session we are going to study about AVL tree. Okay, so let me see whether am I audible and visible or not. 1 second. Yeah, I think I am audible and clearly visible. Okay, let's start. Okay, so today we are going to study about AVL tree. Okay, so we have previously studied about BSTs. Okay, so that is binary search tree. Okay, so the property of binary search tree is that if we have a node, then the nodes in the left subtree will be less than the value of this node, and the nodes present in the right subtree will have the value greater than the node value. Okay, so this is the property of our BST. Okay, but the problem with our BST is that if we have element something like this. Okay, so if we have a list, then our BST will look like this, and it is similar to a list. Okay, so here if we search for an element, if our tree is a skew tree, so this tree is known as a skew tree. Okay, so the time for searching will be order of n if there are n nodes in the worst case. Okay, so to overcome the disadvantage of this, to overcome this disadvantage of BST, AVL tree is introduced. Okay, so let's see what we are going to study in today's session. First, we will see what is AVL tree. Okay, then we will see what is balance factor, what are different types of rotation. So we have LL, RR, LR, and then RL rotation. Okay, then we will see about insertion, deletion in AVL tree. Then we will see how we can search an element in an AVL tree, and we will see the basics of red black tree in today's session. Okay, and then we will see the comparison between AVL tree and red black tree, and after that we will do some gate questions. Okay, so let's start. So what is AVL tree? Okay, so AVL tree is a self-balancing binary search tree. Okay, so AVL tree is a BST. Okay, first of all. Okay, and it is self-balanced. Okay, and the difference between the height of the left subtree and the right subtree is at most 1. Okay, so if I have a tree something like this. Okay, so the height of the left subtree here, it is 2, and here it is 1. So the difference of 2 minus 1 is 1. So the difference between the height of the left subtree and the right subtree cannot be more than 1. It should be less than 1. Okay, and this AVL tree, the name AVL comes from the inventors of AVL tree. Okay, so it is Adelson, Welsky, and Landis. Okay, so the AVL tree name given the from the initials of their inventor's name. Okay, so AVL. Okay, so let's see AVL tree with an example. So let's suppose that we have some values in our tree. Okay, 80, 55, and here it is 35. Okay, so this is the BST. Okay, how we can check whether it is uh, balanced or not, means how we can say that it is a AVL tree. So for that we will check the balance factor of AVL tree. Okay, so here the balance factor of this leaf node is 0, and so balance factor we will study in the later side what it is, but balance factor is height of left subtree minus height of right subtree. Okay, so here there is no left subtree, so here it is 0, and here it is 1, so 0 minus 1, so it is minus 1. Then we have 55, here it is 0, and here the left subtree is 1, and here right subtree is 0, so it will be 1. And here the balance factor of the left subtree is 2 and right subtree is 2, so it will be 0. Okay, 2 minus 2, 0. Okay, so this is the AVL tree with the balance factor. So in BST we only have a node data. Okay, and then we have the left child pointer, right child pointer. But in AVL tree we also have one extra thing, that is our balance factor. Okay, we will augment it with the balance factor, or we can compute it at the runtime also. Okay, so we will see about balance factor. Okay, but first of all, why AVL tree? So as I told you earlier, so the drawback of BST is that if our tree is a skew tree. Okay, so if a tree is something like this, so I have 100 elements, and 1 second, I have 100 elements and all the elements are like this. Okay, and at last we have 100. Okay, so here in this tree, so it is something like a linked list. Okay, because there is no left child, only right child are there for per node. Okay, so there is only one pointer for each node, so it is forming a list, and it is known as a skew tree. Okay, and here if there are 100 elements, then the height of the tree will be 100. Okay, and we know that the BST operations take, so insertion in BST takes order of h time, where h is the height of the uh, tree. So here in this case height is 100, so it will be 100. Okay, so here if there are n elements. Okay, so if we have n elements, so h will be n. Okay, height will be n in a skew tree, and in the worst case it would be order of n. Okay, but the average time complexity of insertion in BST was log n. Okay, but in the worst case we take order n time. So so to overcome this advantage, we introduced AVL tree in which we have the height of the AVL tree always equal to order of log n, where n is the number of nodes in the tree. Okay, so in AVL tree we will always have order log n time for searching, insertion and deletion, and the height of AVL tree will be order of log n also. Okay, so because the difference between the height of left subtree and the right subtree is 1, at most 1, that's why it is log n. Okay, now let's see what is balance factor. So as I told you earlier, balance factor is left height of left subtree minus height of right subtree. Okay, so this is the formula for that. And for AVL tree, the valid balance factor value is -1, 0 and 1. Okay, so let's take an example. So we have a node 45, it has 30, then we have 60, then we have 50, then we have 70. Okay, and here we have only 5. Okay, so here the balance factor of this node, since it has no child, no left child, no right child. Okay, so here the balance factor would be 0. Okay, now we have this node. Okay, so here also there is no left and right child, so here also the height of the left and right subtree will be 0, so it will be 0 minus 0, so it will be 0. Here also it will be 0, so the balance factor of leaf node is 0. Okay, now if we have 30, so 30 has one so if we compute balance factor of 30. Okay, so height of the left subtree is 1, because there is one node after this, and the path the path length of this 30 from leaf node is 1. Okay, minus, and the right node right subtree is 0, so it will be 0, so it will be 1. Okay, so the balance factor of 30 is 1, so we will write 1 here. Now we will compute balance factor of 60. So balance factor of 60 will be height of left subtree minus right subtree. So height of left subtree is 0. So because sorry, the height of the left subtree is 1, and here also the height of the left subtree is 1, because 1 1 node are there. Okay, and it will be 0. So the balance factor of this node will be 0. Now if we compute the balance factor of 45, so the height of the left subtree is 2, as you can see here, because the longest path from root from this node to leaf is 2, of length 2. So it will be 2, and here also in the right subtree it is 2. So it is 2 minus 2, so it is 0. So here also balance factor is 0. So as you can see, all the nodes in this tree have balance factor between 0, -1 and 1. So here in this case all have 0, either 0 or 1. So it is a valid AVL tree. Okay, so we can say that this is a balanced tree. Okay, balanced. Okay, yeah. So this is about the balance factor in AVL tree. Now let's see some questions first. One second. Yeah. So let's see one question. So how many structurally unique BSTs are possible with n distinct keys? Okay. So in BSTs, so suppose that we have n equal to 3. Okay. So how many structurally unique BSTs are possible? So structurally unique means if we have 3 nodes, okay, n is equal to 3. So n is 3. Then this is structurally unique BST. Okay, we can have this also. We can have this type of BST also with 3 nodes, and have this type of BST also with 3 nodes, or we can have this. So there are 1, 2, 3, 4, and 5 unique BSTs are possible with n equal to 3. So n equal to 3, number of BSTs are 5. Okay, so we have drawn all the possible combination here, and if we can if we want to, so here the nodes are unlabeled, so we can label it also. So here it would be 3, 2, 1. Here it would be 1, 2, 3. Here it will be 1, 2, 3. So we have to follow the property of the BST here. Okay, so it will be uh, 3, 1, 2. Okay, here it will be 3. Sorry, here it will be, I think, 1, 3, and 2. Okay, so here 5 structurally unique BSTs are possible with 3 nodes. So if I want to find the number of possible structurally unique BST for n equal to 100, so how will I find it? So for that I have to draw all the possible combination, and it will be very difficult to draw all the possible combination because it can be many. Okay, and for that we have a formula for this. So the formula is something like this. Okay, formula is number of BSTs possible are 2n Cn upon n plus 1, where 2n Cn is the combination. Okay, so this is the formula for our calculation of number of BSTs. Okay, now let's take an example. Let's put n equal to 3 in this formula. Okay, so n equal to 3, so 3 into 2, it will be 6 C3 upon 5, sorry, upon 4, because n 3 plus 1 is 4. Okay, so 6 3 C will be 6 factorial upon 3 factorial upon 3 factorial, and we have 4 also in the divide. Okay, so it will be 6 into 5 into 4, 6 into 5, sorry, 6 into 4, so because 4 is there. Okay, so it will be 5. So hence the answer that we are getting for n equal to 3 is 5, and we know that it is 5 because we have just calculated the BSTs for n equal to 3. Okay, so this is the formula for that to compute it, and you can remember this formula and note it down for this. Okay, so it is also known as Catalan number. Okay, Catalan number. Okay, Catalan's number. Okay, now let's see one more question. So if we want to find the minimum number of nodes in an AVL tree of height 5, so how can we do that? Okay, so if height is 0, okay, So if height is 0, so there is only one possible case because we have one node and it is at level 0. Okay. If height is 1, then the minimum number of nodes would be, there will be one more node and it will be present here, or it will be present here. Okay. So the here in this case it will be 1 minimum number of nodes. Okay. In this case it is 2. Okay. H equal to 2, we have to this. Okay. So here also for h equal to 2, we need at minimum 4 nodes for a valid AVL tree of height 2. Okay. So for height 5, how many minimum number of nodes required? Okay. So for an height equal to 2, we can easily compute it. But for the bigger heights, we have the formula to do it. So it is a recursive formula. So let me write it, number of node for particular height. Okay. So let me write it here. So our it is and denotes the number of nodes, and then we have h, okay, which denotes the height. Okay, equal to uh, height minus 1 plus n of height minus 2 plus 1. So this is the formula, and for n equal to 0 it is 1, and for n equal to 1 it is 2. So as we can see, for height equal to 0 it is 1, and for height equal to 2 it is 2. Height equal to 1 it is 2. Okay. So let me just rub this, erase this. Okay. Now let's compute the height. So let's compute the minimum number of nodes with the given height. So we have h equal to 5 here. So we want to compute n of 5. Okay. So n of 5 will be n of 4 h minus 1 plus n of 3 h minus 2 plus 1. Okay. Now to get n of 5 we need n of 4. So n of 4 will be n of 3 plus n of 2 plus 1. Now to get n of 4 we need n of 3. So n of 3 will be n of 2 plus n of 1 plus 1. Okay. Now for n of 3 we need n of 2, and for n of 2 we have n of 1 plus n of 0 plus 1. Okay. So as you can see here, it is some kind it is the recursive formula, because for sub for h problem we are solving h minus 1 sub problem and h minus 2 sub problem. Okay. So we know that the value of n of 1 is 1, n of 1 is 2, and n of 0 is 1. Okay. So it will be 1 plus 2 plus 1, oh sorry, 2 plus 1 plus 1, so it will be 4. Okay. Now n of 2 is 4, so n of 1 is 2, so it plus 1, so it will be 7. So for height 3 we need minimum 7 nodes. Okay. Now let's see, for n of 4, n of 3 is 7, n of 2 is, n of 2 was 4 plus 1, so it will be 4 plus 7 plus 4 plus 1, so it will be 12. N of 4 is 12, so 12 plus n of 3, n of 3 is 7 plus 1. Okay, so it will be 20. Okay, so the answer will be 20. So the minimum number of nodes for an AVL tree with height is 20. Okay, so 7, and then we have 7 plus 4, 12, and 12 plus 7 plus 1, that is 20. Okay, so here our answer will be 20, and this is the formula to find the minimum number of nodes. Okay, so you can write this formula. Okay, and you can uh, means if the question comes something like this, then you can solve this question using this formula. Okay, now let's see the rotations in AVL tree. Okay, so 1 second. Yeah, so we have 4 types of rotations. So first two rotations are single rotations, and the next 2 rotations are double rotation. So I will tell you why it is single and why it is double. So we have LL rotation, RR rotation, LR rotation, and RL rotation. Okay. So here LL means left rotation. Okay. So it is left rotation. So, and here it is right rotation. Then LR means left right rotation. and RL means right left rotation. Okay, and here it is double, and here first two are single and next two are double. So let's see them one by one. Okay, so first one is LL rotation. So if we have a BST something like this, so if we calculate the balance factor here, so it will be 0, it will be 1, because here left subtree is 1 and right subtree is 0, so 1 minus 0 1. And for 3 it will be 2, left subtree height is 2 and right subtree height is 0, so it will be 2. And we know that the balance factor for a valid AVL tree is -1, 0 and 1. Okay, so it is not a valid AVL tree, so we have to perform rotation to make it a valid AVL tree. So how we will do that? So we will first go to the unbalanced node. So here 3 is the unbalanced node. So we will see, so here left, so it is in the left side and it is also in the left side. Okay, so here the unbalancing that is caused is in the left side. Okay, so for this we will do a LL rotation. So here we will perform the LL rotation. So what will be that LL rotation? So we will move it in this direction. Okay, in the clockwise direction. So here it will be 2 and here it will be 1 and it will be 3. So as you can see, this is also a valid BS tree, and here the balance factor of 1 is 0, 3 is 0 and 2 is also 0, 1 minus 1 0. Okay, and it is a valid AVL tree also, because the balance factor range is from -1 to 0, -1 to 1. So here it is 0, so it is valid. Okay, so this is the left rotation, LL rotation. So whenever we perform inserting some node, or whenever we perform some deletion operation, then our tree get unbalanced and we balance it using this rotation. So if this case arise LL left left, then we will use LL rotation for that. Okay, now let's see RR rotation. So here we only rotate one time, hence it is a single rotation. Okay, now let's see RR rotation. So here in this BST, we have 1, 2, 3, and here the balance factor of 3 is 0, balance factor of 2 is -1, and balance factor of 1 is -2, because right subtree height is 2 and left subtree height is 0, so it is -2. Okay. Now here the it is unbalanced because of the right side. So here it is RR. Okay. So to rebalance it, we will do RR rotation, and for RR rotation we rotate it in the anti-clockwise direction. Okay. So it will be 2, 1 and 3. So here if we compute the balance factor again, so it will be 0, it will be 0 and it will be 0, because height of the left subtree and height of the right subtree is 1 1. So 1 minus 1 0. Okay, so this is the RR rotation, in which if the unbalanced node and the direction is right, okay, means that unbalancing is caused by the right side. Okay, so if it is the right side, then it will be minus. Okay, and if it is caused by left side, then it will be plus balance factor. Okay, you can see. Okay, so now let's see, so it is also a single rotation, as you can see, because we have rotated one time only. Now let's see LR rotation. Okay, so LR rotation means left right rotation. Okay, so here we perform rotation 2 times, hence it is double rotation. Okay, so here we can, when we compute the balance factor, so it is a for 2 it is 0, for 1 it is -1, and for 3 it is 2. Okay, so here the unbalanced node is 3, because -1 and 0 are the valid values for balance factor. So here it is L and here it is R. So now to rebalance it, we will do first RR rotation. Okay, so for LR rotation, we do first RR rotation and then we will do LL rotation. Okay, so here first we will rotate it. So here it will become 3, then it will become 2, and then it will become again when we compute balance factor, so it is 0 1 2, and now we will again rotate it LL. Okay, we will again apply LL rotation, so it will be 2 1 and 3, and if we compute the balance factor again, so it will be 0 0 0. And here in LR rotation, it is a double rotation in which we perform rotation 2 times. So for LR rotation, we perform first RR rotation and then LR rotation. Okay, so you can remember this short notation. First we have to perform RR, then we have to perform LL for LR rotation. Now let's see second of the last rotation, that is RL rotation, that is uh, right left rotation. Okay, so it is also a double rotation. So here if we compute the balance factor, so for 2 it is 0, for 3 it is 1, and for 1 it is -2. So here RL, so we need to do the rotation, so to make it a balanced tree. Okay, so for that we have first we have to do LL rotation here. Okay, so for that we will do LL rotation, and we will uh, rotate 2 and 3. So 2 will come here and 3 will be here. Okay, now here 0 and 1, -1, and it will be -2. Okay, the balance factor. Now we will do the LR rotation. Sorry, now we will do the RR rotation. Okay, so when we do RR rotation, so it will be 2, then we have 1, and then we have 3. Okay, so here if we compute balance factor again, so it is 0, 0, 0. So all are zeros. Okay, and now it is balanced. Okay, so if we have RL rotation, then we need to first perform LL rotation, then R rotation. Okay, so for RL we have LL rotation first and then RR rotation. Okay, so this is about the rotations in the AVL tree. Now let's see how we can insert in an AVL tree. Okay, so if we want to insert in AVL tree, then we have to follow these steps. So for since AVL tree is a BST, so we perform first the standard BST insert. Okay, so the new node will be inserted like we have inserted in the BST recursively. Okay, and then we calculate the balance factor for each node. Okay, and if the balance factor so the if the balance factor is not in the range -1, 0, and 1, then we will try to balance it using the rotations. Okay, so here from this starting a new node, we will travel up and find the unbalanced node that is not that is unbalanced, and perform the rotation, respective rotation, until the tree becomes the balanced tree. Okay, so let's suppose that we have a tree something like this. Okay, and sorry, here it will be 50. So you have 40, 50 is greater than 40, 20 is less than 40, and 10 is less than 40. So it is a valid AVL tree. Okay, here the balance factor is 0, 1, 0, and 1. Okay, so 2 minus 1, it is 1. So it is a valid BST. Now if I insert 5 here, so I want to insert 5. So first I will do the standard BST insert. So I will compare it with root. So root will be compared with 5. Since 5 is less than 40, so we will go to the left subtree and we will compare again with root. So 5 will be compared with 20. So 5 is less than 20. So again it will come to 10, and 10 will be compared with 5. So 5 is again less than 10. So we will go to the left subtree of 10, which is null. So we will insert our node here. So it will be 5. And now if we compute the new balance factor, okay, so the balance factor of 5 will be 0, the balance factor of 10 will be 1, balance factor of 50 will be 0, balance factor of 20 is 2, and balance factor of 40 will be 3 minus 1, that is 2. Okay, so here our tree is unbalanced because the unbalanced nodes are 20 and 40. Okay, so the first we have inserted 5, so we will go upwards. Okay, and we will see the unbalanced node. So when we go up, first node that is unbalanced is 20. So we will come here in 20 and we will see so why it is unbalanced, means what is the reason for this to be unbalanced. So we see that here the left subtree has balance. So here the left subtree has greater height than the right subtree. Okay, so here it is LL rotation. So because it is in the left hand side, and here the balance factor is also positive. Okay, so we know that the height of the subtree here is more than the height of the right subtree. So the rotation that we have to perform is LL rotation. Okay, so LL rotation. So we need to perform here the LL rotation. So rotation. So if when we perform this LL rotation, so our new tree will be 40, 50 will be as it is, and here the new node will be, so 10 will come up, okay, and 20 will be here, and 5 will be here. Okay, so let me just do something like this. If T1 is there, then we have T2, and if it is T3, so after LL rotation, it will be T2, T1, and T3. Okay, so here 10 will be here, 5 will be here, and 20 will be here. So when we compute the balance factor again, so it will be 0, 0, 0, 0, and here it will be 1. So now the balance factor is in the range of -1, 0, and 1. So it is a valid AVL tree. So in this way, we are going to perform the insertion in AVL tree. Okay. So now let's see one example. Okay. So we have this numbers and we want to construct a AVL tree from this sequence. Okay. So first node will be there. So our initially our tree is empty. So it will be 63 when we insert it. So when we compute the balance factor, it will be 0. Okay. Now we will insert 9. So we will perform this standard binary search insertion. That is 9 will be compared with root and it is less than root. So it will be 9 will be here. Okay. And again, we will compute the balance factor. So it will be 0. It will be 1. So it is again balanced. Now we will insert 19. So 63, 19 is compared with 63, so it is less, and it is when it is compared with 9, so it is also less. So 19 will be inserted here. Okay, so when 19 is inserted here, okay, now we will compute the balance factor again. So it will be 0, -1, and 2. Hence we can see that it is LR rotation. Okay, so we have to rotate it twice. So first it will be 63, then 19, and then 9. So 0, 1, 2, and then we will perform. So first we have performed RR rotation, now we will LL rotation. So it will be 19, and then 9, and then 63. Okay, so after 3 element insertion, our tree looks something like this. Now when we 27, so 27 will be compared with 19, so it is less than greater than 19, so we will go to the right side. Here 63 is greater than 27, so 27 will be inserted here. And when we will compute the new balance factor, so it will be 0, it will be 1, it will be 0, and it will be -1. Okay, now let's insert 18. Okay, now 18 will be compared with 19. So 19 is greater than 18, so 18 will go to the left subtree. So sorry, it will go to the left subtree, so it is 9. So 9 will be compared with 18, so 18 is greater than 9, so 18 will be inserted here in the right of 9. Then we have 63, and then we have 27. Now when we compute the balance factor, so it is 0, it is 0, it is -1, it is 1, and it will be 0. Okay, now let's insert 108. Okay, so here we have 19, and then 9, then 18, then 63, and then 27. Now we are going to insert 108. So 108 will be compared with 19, so it is greater than 19, so we will come in the right subtree, and in the right subtree 63 will be compared with the 108. So 108 is greater than 63, so it will be here. So 108 will be in the right of the 63. And now again when we compute the balance factor, so it is 0, it is 0, it is 0, it is 0, it is -1, and it is 0. So again our balance, so we need no need to perform the uh, rotations. Okay, now let's insert 99. Okay, so let me just erase all this. Okay, one second. Okay, so now I want to insert 99. Okay, so let me draw our so we have 19, then we have 9, then we have 63, here we have 18, and then we have 27, and we have 108. Now 99 will be compared with 19, so it is greater 63, so it is greater than 63 also. When compared with 108, so it is not greater than 108, so it will come here. And now when we compute the balance factor, so it will be 0, it will be 1, it will be 0, it will be minus 1, it will be 0, it will be minus 1, and it will be 3 and 2, so it will be minus 1. Okay, so again our tree is balanced, so we no need to perform any rotation. Now when we insert 81, so 81 will be inserted. So when we insert 81, so 81 will be inserted here, means first we will compare with 19, so it is greater than 1963. Then we will go to left of 63, so it is 108, and it is less than 108, so we will go to 99, and it is less than 99, so it will come here. Okay, again we will compute the balance factor here, so it will be 0, it will be 1, it will be 2, it will be 0, and it will be minus 2. Then we have 0, minus 1, and here the path length is 4, and here it is 2, so it will be minus 2. Okay, so as you can see, here there are 3 nodes that are unbalanced, so we have to perform here the rotation. So we will go, so 81 is inserted, so we will go upwards and we will see the first unbalanced node, so it is 108. So here we can see that here LL rotation is there, so we will perform the LL rotation here. So it will be 19, then we have 9, then 18 will be here, and after that 63 is there, 27 is as it is, and then we have 108 was there, but after LL rotation it will be 99, and 108 will be in the right, and 81 will be in the left, okay, of 99. Now let's compute the balance factor again. So here it is 0, here it is 0, here it is 0, here it is 0, and then here it is minus 1, so 0 and 2, so 1 and 2, so it is minus 1, here also 0, here also minus 1, and here it is 2, and here it is 3, so it is 2 minus 3, so it is minus 1. So now our tree is balanced because the balance factor is in the range 0, minus 1, and 1. Okay, so after performing the insertion of this many elements, our final tree will look something like this. Okay, so this will be our final tree. Okay, yeah. So in this way, we are going to insert the elements in the AVL tree. Okay, so 1 second. Yeah. So now let's see the deletion in AVL tree. Okay, so how can we perform deletion in an AVL tree? Okay, so the deletion is performed in the same way as the insertion. First, we need to perform the standard BST delete. Okay, and for the sorry here for the node that is to be deleted, for the node to be deleted. Okay, and calculate the balance factor for each node, and starting from the new node, travel up and find the node that is unbalanced and perform the respective rotation and rebalance the tree. So let's suppose that we have this tree. Okay, so if we compute the balance factor, so it will be 0, it will be 1, it will be 0, it will be 2 minus 1, so it will be 1, it will be 0, it will be 1, and here 3 and 2, so it will be 1. So as you can see, this tree is balanced, and now let's perform some deletion operation. So let's delete 55. So 1 second. Okay, so delete 55. Okay, so when we delete 55, so first we will compare 55 with 50. So 55 is greater than 50, so we will go to right subtree. So 60 is less than 55, so we'll go to the left subtree, and here 55 is there. And now we will perform the standard BST delete. So we know that we have 3 cases in case of BST delete. First, node has no children. Okay, no child, no children. Then 1 child, and then 2 childrens. Okay, so if a node had 2 childs. Okay, so for the node which is having no children, then we have to just delete that node. Okay, so we will just delete that node, so 55 will be deleted, and it will be 50, 40, 60, and 30, and then 45, and then 10. Okay, and now we have deleted 55. Now we will compute the balance factor again, so it will be 0, 1, 0, and then 1, 2 minus 1, and then it is 0. And now when we compute the balance factor of for 50, so it will be 3 and 0. Okay, so it will be 2. 3 minus 1, so it will be 2. Okay, so here this node is unbalanced. Okay, so now we have to perform the so we have to balance. For that we need to perform the rotation. Okay, so as you can see here, the rotation that we have to perform is LL rotation, because this node is unbalanced. Okay, 50. And after performing the rotation, our tree will look something like this. So 60 will be there. Okay, so the 45 which is in the right of the tree will come in the left of 50 now. Okay, and now when we compute the balance factor, so it will be 0, it will be 1, and it will be 0. So now our tree is balanced after deletion of 55. Okay, so in this way we are going to delete element in a in a AVL tree. Okay, so first we perform the standard BST operation, and then we compute the balance factor for each node, and we see which node is unbalanced, and then we perform the rotation according to the unbalanced factor, because here it is a positive and it is 2, so we know that the rotation that is caused is from the left side, because the length of the uh, left subtree length so height of the left subtree is more than the right. Okay, since it was positive. Okay, so we performed LL rotation here. Okay, now let's see the searching in searching in AVL tree. So searching in AVL tree is similar to the BST, so the same code is there. And here if okay, suppose let this is our tree. Okay, 50 and 100, and here it is 45, and it is 95. Okay, so as you can see, this is a AVL tree, and balance factor is 0, 1, 0, minus 1, 0, 0, 0, and minus 1. Okay, and it is a BST also. Okay, so if I want to search for 45, so I will go to the root, I will compare it with root. Since I will compare with root, so root value is 40, and when compared it with 45, so it will be root value is compared with 45, so it will be 40 less than 45. So we will go to the right subtree. Okay, so 40 root data is 40, and it is 50, key is 50, so we will go to the right subtree. Okay, sorry, key is 45. So we will go to the right subtree, and in the right subtree it is 50, and 50 is again compared with 45. And since 50 is greater than 45, so we will go, this if condition will not satisfy, we will go to the left of it, and here it is 45. Now 45 is compared with 45. So 45 is equal to 45. So yeah, so our it will return 1, and again the call will go to 50, and it will also return 1, and it will return 50, it will return 1 to 40 also, and at last we will get 1 as a output. So 1 means successful search. Okay, so 1 means successful search, and 0 means unsuccessful. Since the element was present in our BST, hence we 1 is written. If it is not present, then 0 will be returned. Okay, so as you can see here, in any case in AVL tree, the searching will take order of log n time. If there are n nodes in AVL tree, then searching will take order of log n time in the worst case. Okay, so here I have used order rotation, not theta rotation notation. So order notation is used, that means it is the upper bounded. So in the worst case, we need to spend log n time to find any value in the AVL tree. Okay, yeah. So this is about the searching in the AVL tree. Now let's see what are red black tree. So red black tree is also a self-balancing binary tree, binary search tree. So here, so they are also self-balancing binary tree. Okay, but here we don't use balance factor. So balance factor is not used here. Here instead we use a extra bit per node, that is color. So a node can either be red or it can either be black. Okay, and these are the following conditions that needs to be satisfied. Okay, so for red black tree, it is a binary search tree with each node has some color, that is red and black, and the following properties should be satisfied. Okay, so let's see the properties. So first property is every node is either red or black. Second, root is always black, and the leaf node, which is nil or null, it will be black. Okay, so root and leaf nodes will be black. So leaf nodes here are not leaf. Okay, so they are the null values. So if the node is there, so it is so we consider it as a leaf node since it has no childs. So but here the leaf means this null nodes. Okay, okay, so they are black, so we will consider them, this null node, as black. Then if a node is red, then both of its children are black. Okay, so as you can see here, if the node is red, then both of its children would be should be red, should be black. Okay, and for each node, all the simple path from the node to the descendant leaves contain the same number of black nodes. So here in the red black tree, from the starting from every node, if we see every path, so from 7 to this leaf 3, there are 2 black nodes. If we see from 7 to 8, there are only 2 black nodes in this path. Okay, in this path also there are only 2 black nodes, and in this path also there is only 2 black nodes. So every path from a node to the leaves will have same number of black nodes. So this is the main property of BST. So this property help us to maintain means uh, what we say to maintain a height of log n. Okay, so for because of this property, number of black nodes, our red black tree will not have a height more than log n. Okay, so in AVL tree we use balance factor. So we say that a balance factor should be -1, 0 and 1, but for red black tree we need to satisfy this property. The number of black nodes should be same in every path from the node to the leaves. Okay, yeah, so this is about the red black tree. So we will not going to cover the insertion and deletion of red black tree because they are not in the gate syllabus. So this is just for your reference. So what are red black tree, and these are the properties of red black tree. Okay, and so it is also a self balancing binary search tree like AVL tree, but here color is used instead of balance factor. Okay, now let's see the comparison between red black tree and AVL tree. Okay, so AVL tree provide faster lookups. Okay, so because AVL tree is more strictly balanced than red black tree, means because in AVL tree the height is at most 1 between the last two levels. Okay, but in red black tree, um, it is not that strict as AVL tree, means it can have, if the color property and the black node property, number of black nodes property satisfy, so it can have means a difference of more than 1 or more than 2 in the height of the last level and the uh, means the last level and the upper levels, difference of 2. But that is not the case in AVL tree because balance factor is -1, 0 and 1 in case of AVL tree, and in red black tree only the color property and number of black nodes. Okay, black nodes should be satisfied. So these two properties should be satisfied in red black tree. So it is less strict than the AVL tree in terms of the balancing. Okay, means it is balanced, but it can have more little bit more height than the standard AVL tree for the corresponding nodes. Hence, AVL tree performs faster lookups than red black tree. Okay, but the advantage of red black tree is that it provides faster insertion and removal operation than AVL tree, because in red black tree there are fewer number of rotations that are performed compared to AVL trees. Okay, so red black tree. So if we compare number of rotations, okay, in red black tree it is fewer. Okay, and in AVL tree it is more compared to red black tree. Okay, and third is the balance factor. AVL tree stores balance factor or heights with each node, so we have to augment the our struct that we defined for our tree with the balance factor and the height. Okay, so we have data, then we have pointer, left pointer, then right pointer. In standard BST also we have balance factor and height if we want to efficiently make AVL tree and do the operations on it. Okay, but in AVL in red black tree we required only one bit of information per node, and that is the color. Okay, so in red black tree we only need to store one bit of information, that is color. Okay, and red black trees are used in map, multi-map, multi-set in C++. Okay, so we have libraries like map, multi-map, in which red black trees are used. Okay, so map is a data structure in which we store the data in form of key comma value. Okay, and we retrieve the data using key. Okay, and then we have multi-map in which we can have multiple duplicate keys. Okay, and then we have multi-set in C++ in which we have duplicate keys in the set also, and this are implemented using the balanced balanced binary search tree, that is red black tree. Because here if we perform insertion and deletion, then it will be faster as compared to AVL tree. So we can also implement this data structures. So this library is using AVL tree also, but in AVL tree we need to perform more number of rotations here. Okay, and AVL trees are used where we need fast lookups. So like in databases where the fast retrievals are required. So AVL trees are used there. Okay, so this is the comparison between AVL tree and red black tree. Now let's see some gate questions. So this question was asked in gate CS 2020. So it was asked in the previous year. So previous year means okay. So in this question we have to find the worst case time complexity of inserting n square elements into a AVL tree with n elements initially. Okay, so we have an AVL tree with n nodes. AVL tree with n nodes. Okay, and now we want to insert n square elements more. Okay, and we know that insertion takes order of log n time in AVL if n nodes are there. Okay, so for the first insertion, it will take log n time. For the second insertion, it will take uh, n plus 1 time, because now there are n plus 1 nodes. For the third insertion, it will take log n plus 2. Then for after n square insertions, so it will take log n plus n square time. And we know that log n means log n, and log n plus 1 also means the same, means because we consider here the worst case. So n plus 1 means log n only, n plus 2 is also log n, and n plus n square will be log n square. And if we use the log property, so 2 will come here, so it will be 2 log n, and it will be order of log n only. Okay, and since we have performed n square insertions, okay, and each insertion is taking almost in the worst case log n time, so for n square it will be n square into log n. So this should be our time complexity, worst case time complexity for inserting n square element into the AVL tree with n elements initially. So the correct answer would be C. So here we required n square log n time. Okay, so n to the power is absolutely wrong because we don't require this much time. Okay, and if we consider it as a binary search tree, then in the worst case it will take n cube time. But here we are considering it as a AVL tree, so it will take n square into log n time. Okay, so the correct option is C. Okay, now let's see one more question. So this question was asked in GATE 2012, in which we have to find the worst case time complexity to search an element in a binary search tree with n into 2 to the power n element. So here they have told balanced binary search tree. So it can be so balanced binary search tree. So there are two. First one is AVL and second one is red black. Okay, and in AVL, insertion, search, deletion all take log n time, and in arbitrary also we need all the operation are done in log n time only. Okay, in the worst case. So here I have used ordered notation. So we are talking about the worst case here. So both arbitrary and AVL tree has in the worst case log n time, and the just the number of rotation in AVL tree after insertion and deletions are less compared to AVL tree. Okay, in arbitrary. So arbitrary has few rotations compared to AVL tree. So this is the main difference. And okay, so here it is balanced binary search tree, so we can assume it can be either AVL tree or arbitrary, and we know that in the worst case it will require log n time if n elements are there. In our case, it is the number of elements are n into 2 to the power n, so we just have to take the log of it, so it will be n into 2 to the power n. Okay, yeah, so order of this will be our answer. And if we simplify this, so it will be, if we use the log property, so log AB is log A plus log B. Okay, and log A to the power B into log A. Okay, so we have to use these two properties. Okay, so here it is log n plus log 2 to the power n. So this n will come here, so it will come here, and log 2 is as you can see, log 2 is 1. Okay, so log 2 base 2 is 1, so it will be 1 into n, so it will be log n plus n. And we know that n has higher n is asymptotically higher than log n, so it will be order of n. So hence our answer for this will be C, and it is n. Okay, so order of n will be our answer. So here they have asked for worst case time complexity, but they have used theta notation. It should be order notation here, but since this was taken from the GATE paper only, so here the correct answer is order of n. Okay, since we required order of n time for n into 2 to the power n elements. Okay, yeah. Now let's see one more question. So this question was asked in GATE 2009. So we need to find the maximum number of maximum height of any AVL tree with 7 nodes, and assume that the height of the tree with a single node is 0. Okay, so we have studied one formula previously. So here n of 0 is 1, n of 1 is 2, and for n of h, it will be n of h minus 1 plus n of h minus 2 plus n plus 1. Okay, so plus 1. Okay, so if we put h equal to 3, so it gives us uh, n of 2, n of 1 plus 1, and n of 2 value was 4, and n of 2 1 value is 2, and it is 1. So here for minimum number of nodes for height equal to 3 was 7. And we have seen this when we have seen the formula, when we have seen this formula. Okay, and we know that with the height 3, the number of nodes, minimum number of nodes will be 7. So here they have asked us to find the maximum height of any AVL tree with 7 nodes. Okay, so with 7 nodes, the maximum height that it can have will be 3. Okay, because for height h equal to 3, we require minimum 7 nodes, and for 7 nodes, maximum height that we can get is 3. So correct answer here will be 3. Okay, so you can check it by drawing also. So since it is h equal to 3 only, and it is only 7 nodes, so you can check it by drawing the tree also. So here it is for 4, so here one element should be there, and so here it can be here. Okay, and here it should be 1. Okay, so if you consider this tree, it contains 7 nodes. So 1 2 3 4 5 6 7, so it is 7, and the height of this tree is 3. Okay, so the correct answer for the maximum height that we can get is 7, because if we do something like this, if we erase this node and put here, so height is 4, but it is not a AVL tree. Okay, because the balance factor is not stable here. Okay, so here it is unbalanced. Okay, so the correct answer for this question will be h equal to 3, that is the correct answer is 3. Okay, now let's see one more question. So this question was asked in gate 2008 IT, in which we have to tell which of the statement is correct. So let's see all the statements. So the cost of searching an AVL tree is theta log n, but that of a binary search tree is order of n. So we know that the cost of searching in AVL tree is log n, so it is correct. And but the uh, cost of searching in the binary search tree is order of n, so it is also correct, because they are talking about the worst case here. So our first statement itself is correct. Okay, and since it is a multiple choice question, so if one statement is correct, that means all the other statements are false. So our correct answer would be A. But now let's see the other options also, in which so here we got lucky that our first statement is correct. Okay, now let's see the second statement, in which the cost of searching for AVL tree is log n, theta of log n, and that of a complete binary tree is n log n. So here it is false, because for a complete binary tree, it will be log n only. So this option is false. The cost of searching a binary search tree is log n, but the AVL tree is order theta of n, so it is also false, because it is log n. And the cost of searching of AVL tree is n log n, so it is false. And binary search tree is order of n. So here it is, in this statement AVL tree, they are telling that theta n log n is the answer. So it is not the cost of searching. The cost of searching for AVL tree is log n. So our correct option will be A only. Okay, and all the other options are wrong. Okay, so this is it for today's session. Okay, so thank you for watching. Okay, so let me see if there are any question in the comment section. So there are no questions. Okay, so yeah. Okay, so thank you guys.